So if I do the PQ, right, and again, this is U. It was told to us this is U. So I'm going to write it like this, U. And because I know the initial point and the end point, PQ, then actually you can also see it written like this, PQ, with that little arrow on the top of it too. That means the vector that starts at point P and it ends at Q. Okay. Now, in order to use the distance formula to do that, then the distance formula would tell me x2 minus the square root of x2 minus x1 squared plus y2 minus y1 squared, which would look like this. 3 minus 0 squared plus 2 minus 0 squared, which is 9 plus 4, the square root of 13, the square root of 13. Okay, if we did the same thing for the v, right, then it would look like this. V, the vector v, is this RF, and that will be 4 minus 1 squared plus 4 minus 2 squared, which again will be 3 squared plus 2 squared, which is 13, right? So their lengths are the same, so we would say that their magnitude is the same. Now, the way we symbolize magnitude, if you want to find the magnitude of a vector, then you write it like this. The vector is inside kind of a double absolute value symbol, right? The double absolute value bracket. 2 straight lines on either side. That means magnitude. It means the magnitude of. Okay, so in order to show that these two vectors are equal, that they're the same, we have to show the magnitude is the same, and we did that by using a distance formula twice, right? What could we do that would represent whether they have the same direction? What quantity that we've dealt with lines before might indicate direction? Means the reason why you've been taught it about 4 times. Somebody got a cell phone to turn off? Okay. How about slope? Right? Remember that? If you did the slope between these 2 points, right, that would be the difference in the y's divided by the difference in the x's. Right? This slope would have been 2 divided by 3. Change in y divided by change in x. y2 minus y1 over x2 minus x1. What about this one on top? 2 over 3 again, right? 2/3. So by checking the slope, we could say, yeah, they have the same direction too. So the only thing that needs for these to be equal vectors, for u to equal v, is they have to have the same size and direction. Clearly, they're not in the same place. These directed line segments are not in the same place in the plane, right? But vectors don't have a position. That doesn't have to be the same. Now, so you could take a vector, any vector anywhere, and you could bring it back to the origin. If you do, that's called the standard position. Any vector that starts with its initial point on the origin, that's called standard position.